Section 1.1, Inductive Reasoning. To analyze and use patterns or relations. Let's start by defining inductive reasoning. This is reasoning that is based on patterns you observe. In other words, this is based on your past experiences. For example, if your mother makes eggs every Friday morning, then as Friday approaches, you will make a conclusion that she will make eggs. Now, making that conclusion is called a conjecture. A conjecture is a conclusion reached using inductive reasoning, which is based upon your past experiences. Mathematically, if you observe a pattern in a sequence, you can use inductive reasoning or experience from the past set of numbers to tell what the next terms in that sequence will be. Let's take a look at some examples. Find a pattern for each sequence. Use the pattern to show the next two terms. Here, we have 1, 3, 9, 27. Now, all we have to do is determine what pattern is being used to generate the next term. Here, 1 times 3 is 3, 3 times 3 is 9, 9 times 3 is 27. Therefore, 27 times 3 will give us the next term, which should be 81. Then, we would take 81 times 3 and get 243. And then this sequence would continue by multiplying by 3. Example 2 gives us 5, 1, 1/5, and 125. Therefore, this looks like I'm dividing by 5. 5 divided by 5 would give us 1. 1 divided by 5 is 1/5. 1/5 divided by 5 is going to be 1/25. 1/25 divided by 5 is going to give me 1 over 125. And 125, again, is going to give us 1 over 625 when dividing 1 over 125 by 5. Our next sequence, AA, but then we can tell that this is B and B, but the B is flipped, and then the C and the C is flipped, and the D and D is flipped. Therefore, my conclusion or conjecture would be that I have E, and then E is flipped, and then F is flipped. The next sequence shows a circle with a segment off to the right, then to the bottom, and then to the left. Therefore, my experience or conjecture would be that the figure repeats with a circle with the segment to the top, and then a circle with the segment to the right. Example 5 shows 0.2, 1.2, 0.3, 1.3, 0.4, 1.4. Therefore, my conjecture would be 0.5, 1.5, and if I needed to continue, it would be 0.6 and 1.6. Example 6 shows a triangle with a red segment at the top. Then the triangle is rotated clockwise 90 degrees with 2 segments. Another rotation of 90 degrees clockwise with 3 segments. Therefore, I'm going to conclude if I rotate this figure 90 degrees clockwise again and add 4 segments, I'm not so concerned that it's not in red. And then my next one would be another 90 degrees clockwise, but the figure would have 5 segments. Example 7. 3 times 5 is 15. 33 times 5 is 165. 333 times 5 is 1665. 3,333 times 5 is 16,665. Therefore, 33,333 times 5, I would expect to get 166,665. And my second term would be 333,333 times 5. And my conjecture or conclusion would be 1,666,665. With inductive reasoning, not all conjectures turn out to be true. And if we recall from our first case I told you about your mother making eggs every Friday, you may wake up one Friday morning and she is serving pancakes for breakfast, even though she may have served eggs 10 weeks in a row. Therefore, experiences can be incorrect. And when we talk about inductive reasoning, To prove that a conjecture is false, all you need is a counterexample. One counterexample can prove your conjecture false. A counterexample is an example for which the conjecture is false. Let's take a look at two examples. We want to find one counterexample to show that each conjecture is false. Number one, the quotient of two fractions is smaller than either fraction. For number one, I have two fractions. I used 1/2 divided by 1/2. When we simplify this, this is 1/2 divided by 1/2, which equals 1/2 times. We find the reciprocal of the second fraction, which is 2/1. Then we simplify to get 1. And in this situation, they want the quotient of two fractions is smaller than either fraction. And here, the quotient of these two fractions is actually larger than both of these fractions. Therefore, this is one counterexample, and this conjecture is false. In example 2, the conjecture is the difference of two integers is less than either integer. Well, let's take a look at a counterexample. 3 minus a negative 2, and when I simplify, this is actually going to be 3 plus 2, which is 5. And here, it wants us to say that the difference of two integers is less than either integer. I have an integer of 3, the difference, and another integer, which is a negative 2. And therefore, my solution is 5. 5 is actually greater than both original integers that I started with. Therefore, that is a counterexample to the conjecture, and therefore, my conjecture is false.